So we would like to evaluate the function 2 divided by x squared minus 1 from the bounds 2 to 7. And we're also given an identity here, and we are asked to verify that 1 divided by x squared minus 1 equals the partial fraction decomposition of that function. And I think the reason that they've given this to us is so that we may supplement this expression in place of this one later during integration. So the first thing I'm going to do here is I'm just going to solve this algebra, and I'm going to prove that this right here is equivalent to 1 divided by x squared minus 1. So let's just do that real quick, clear up any confusion about it. And the way I'm going to do this is I'm just going to make a common denominator and distribute some of the coefficients, and it should be pretty quick. Okay. All right, and there you have it. X squared minus 1 over x squared minus 1 is equivalent to 1 over x squared minus 1. So hopefully that all made sense. Just a nice little bit of algebra to prove this before we use this identity during our integration. So I'm going to go ahead and delete all of this so that we have some more room. Okay, now that we've proven this identity, we're going to go ahead and write our integral. And right away I notice that there is a 2 here. And since it's in the numerator with nothing else, we can kind of see that it's actually a coefficient of the function 1 over x squared minus 1. And once we see this, we immediately should kind of reference the identity that we previously proved, and we're going to exchange the actual function with this expression right here. All right, so what is the next step from here? Well, it would be quite a mess to try to integrate this, just due to all the moving parts. But the first thing that we can do without any U-substitution is we can use the properties of integrals in order to re-express this statement as the sum of two integrals. So let's go ahead and do that. And just as we did in the first step, we should definitely remove this coefficient from the integral to make integrating easier on ourselves. So I'm going to go ahead and rewrite this with all of the coefficients on the outside of their respective integrals. Okay, so we can't really integrate this, or rather we could integrate this, but it would be a very long process. And the whole purpose of this problem itself is just to kind of get you thinking about the appropriate situations to utilize U-substitution to make the whole process of integrating easier on yourself. So we're going to hop on over to U-substitution land, where we can kind of look at this on its own without any of the reduction that we did here. All right. So welcome to U-substitution land, where everything is dark. But not really, because it's actually a lot easier. So let's define what our U's are going to be here. So I think the things that we should really deal with first are these expressions right here and here, because these are the things that are tripping us up from integrating and preventing us from actually doing things properly. So I'm going to say that U1 is equal to x minus 1, and that U2 is equal to x plus 2. So with this in mind, du1 is equivalent to the derivative of x minus 1 du2 is equal to the derivative of x plus 1. And in both of these situations, the constant here isn't really important, as the derivative of any constant is 0. So really we're just looking at the derivative of x, and the derivative of x is always going to be 1. So we have proven a relationship here that du is equal to 1 times dx, which is very nice when we're doing U-substitution, because it allows us to very quickly replace dx with du without any type of reducing. So let's go ahead and try to put u where it belongs. Oh, whoops. Okay. So now that we have our expression in terms of u, there's actually one more thing that we have to do. See, the bounds 2 to 7 were respective to x, and now that we've re-expressed the function in terms of u, we actually need to adjust those values to reflect what u is. And here we said that u, or u1, is equivalent to x minus 1, and u2 is x plus 1. Oh, sorry about that, that should be a 1. So we need to take the a and b value of each one of these integrals, and we actually need to correct them. So we're going to re-express this as 2 times 1/2, the integral of 2 minus 1, which is 1, and 7 minus 1, which is 6, times 1 over u. And then for u2, we said it was x plus 1, so we're going to add 1 to a and b of this integral. Okay, and I'm going to make a little division line here, so we're going to start moving this way with our reduction. So the next step we're going to do is we're actually going to evaluate the integrals, and the integral of 1 over any variable is equivalent to the natural log of that variable. So I'm going to rewrite the integrals in the terms of natural log as opposed to keeping them as 1 over u. Now let's just check our parentheses here. I think we actually need one more. Okay, so just like we would evaluate any other integral using the fundamental theory of calculus, we now need to really look at those bases and think about what the sum of all of the area underneath the curve from 1 to 6 and 3 to 8 is. So we're going to say that this is 2 times 1/2 times the natural log of 6 minus the natural log of 1 minus 1/2 times the natural log of 8 minus the natural log of 3. Okay, so there's another really nice thing happening here. And you notice that both this part of the expression and this part of the expression is multiplied by 1/2. So because they both have the same denominator when that 1/2 is distributed to each one of these terms, we can actually re-express this as a numerator divided by 2. So I'm going to go ahead and do that real quick. Okay, there we go. And that's all going to be over 2. And then very, very nicely, we have our coefficients canceling out here. And we have the expression natural log of 6 minus the natural log of 1 minus natural log of 8 minus natural log of 3. And the natural log of 1 is e to the 0th, which is just 0. So we can just say that this is the natural log of 6 And then using the properties of logarithms, we can re-express this as the natural log of 8 divided by 3.